So optimisation is where we take our differentiation skills and we apply them in real life practical problems. For example here, we have a farmer who has 500 metres of fence in his shed and he wants to build a rectangular enclosure for his sheep. And he wants the enclosure to have as much area as possible, theoretically, to maximise the number of sheep which he can pack into that enclosure. A couple of options for him. He could build a rectangle which has dimensions of 50 metres in width and 200 metres in length. So he's used his 500 metres of fence there. Now the area that he'll obtain here, just being the length times the width, so 50 times 200, would be 10,000 metres squared of area. Another potential option for him would be to build a rectangle that has slightly different dimensions. This rectangle might have a width of 100 metres and a length of 150 metres. So again, he still used his 500 metres of material, but this time his area is going to be 100 times 150, so 15,000 square metres. So we can see that the rectangle on the right at the moment is optimal for his area. He's got more area in the rectangle on the right, still using the same amount of material. Now we could continue to sort of trial and error this, and it probably wouldn't be too difficult to find roughly where the maximum amount of area is going to be. But it would be pretty cool if we could do this using calculus. So we come down here. We know that the length, so 2 lots of the length plus 2 lots of the width, so that's the perimeter of a rectangle, so just 2 widths, 2 lengths, add them together, you get the perimeter of a rectangle. That has to be equal to 500 because that's the amount of material that he has. So I can rearrange this to get an expression for L in terms of W. What I mean by that is that if I subtract 2W from both sides, I get this expression, and so L is just 250 subtract W. So that's an expression for my length in terms of my width. So for a rectangle with 500 meters of perimeter, the length will be equal to 250 minus whatever the width is. Now the area of my rectangle, that is equal to length times width. Okay, but I know that the length is equal to 250 minus the width. So if I substitute that in for L multiplied by my width, and I expand these brackets out, I end up that the area is equal to negative W squared add 250 W. And that's what my area is equal to strictly in terms of the width of my rectangle. Now, if I want to know when this area is at a maximum, I would want to differentiate it and solve when it's equal to 0. So we're looking for a critical point. We're looking for a maximum here. So this is what my area is equal to. Now, if I differentiate my area with respect to my width, I end up with negative 2W plus 250. And I want to know when that is equal to 0 because that's going to give me any critical points. And if I solve this, so we add 2W to both sides, so we soon see that W is equal to 125 meters. So we can check that this is a maximum by differentiating again. So we use the double derivative test. So the second derivative would just be negative 2. So we're just differentiating this bit. And well, it doesn't matter what my value for W is. Negative 2 is always negative, which means I have a maximum. So this width at 125 meters maximizes my area. And if the width is 125 meters, then my length has to be 250 minus 125, which is also 125 meters. So I actually end up with a square. So this would be my enclosure with all equal sides of 125 meters. And you can check that if you add all of those sides together, you still use the 500 meters of fence, and the area that we get in this case, being the length times the width, is just 15,625 square meters. So you can see that that number there is bigger than both of these numbers. So our square here would maximize his area. So these would be the dimensions that he should build his sheep enclosure with. Let's look at another example. So we'll come over here. We have Hugo, who is wanting a cylindrical rainwater tank for his back garden. Now, the tank that he's looking for needs to hold 30,000 litres. So the bigger the tank, the more it's going to cost him, and his budget is to get a 30,000 litre tank. So 30 cubic metres is the conversion there. Hugo is concerned that the tank may rust, so he intends to cover the entire tank in a protective paint coating. So here we're looking at the surface area. To cover the entire tank in a coating, so to paint an entire 3D object, you're looking at the surface area, all of the area on the outside. But unfortunately, this coating is expensive. So he wants to get a 30 cubic meter water tank that minimizes the surface area. We want the surface area to be as small as possible, so he uses the least amount of paint. So a few options for him. He could build a cylinder that looks something like this. Oh, so cylinder number 1, so a little short and fat one, or a tall, skinny cylinder. Now, the dimensions of the cylinder on the left could be that we have a radius here of 2 meters and a height here of 2.39 meters. And the total area that we would get there would be just the volume that we would get there, would be pi r squared times h. So that's your volume for a cylinder. And if you substitute in your value for r to be 2 and your value for h to be 2.39, you would get 30 cubic meters, which is exactly what we need. So that would be an appropriate dimension of a cylinder. Likewise over here, you could have a radius here of 1 meter and the height 9.55 meters. And you can check there that the volume being pi r squared h is also equal to 30 cubic meters. So both of these cylinders are acceptable for his 30,000 litre water tank. However, let's see how the surface area compares between these two particular cylinders. So the surface area of the one on the left, the formula is 2 pi RH plus 2 pi r squared. So if we put our values for r and h into this equation, and you can do that, and you should get that you get 55.17 square meters of surface area. You can do the same on this cylinder on the right, the tall skinny one, and using the same formula but different values for r and h, you should see that you get 66.29 square meters. So I'd encourage you to check that. So we can see that the cylinder on the left with these dimensions would be far more favorable for him because there is less surface area, so less painting for him to do, which is going to be cheaper. Now, there are a set of dimensions which are completely optimal, and we're going to use calculus to solve for that. So, we know that the volume of the cylinder is pi r squared times h, and that has to be 30 cubic meters because that's the water tank that he was looking at, a 30 cubic meter water tank. So I can get an expression for h here in terms of r. So h is equal to 30 divided by pi r squared. Now the surface area of the water tank is what might change, and that's given by 2 pi RH plus 2 pi r squared. And well, I've got an expression now for h in terms of r. So everywhere I see a h, I'm going to put this 30 divided by pi r squared in. So I get 2 pi times r times 30 over pi r squared plus 2 pi r squared. And if I simplify this down a little bit, I just get 60 over r plus 2 pi r squared, or I could just write that as 60r to the minus 1 plus 2 pi r squared. So that's my new expression for my surface area in terms of the radius for a water tank that is 30 cubic meters in volume. That would be given by this expression. Now, I want to know what radius is going to minimize the surface area. So if I differentiate my surface area with respect to the radius, I get negative 60r to the minus 2 plus 4 pi r. And well, if I rewrite this as negative 60 over r squared plus 4 pi r, that's the derivative of my surface area with respect to the radius. And I want to solve for when that is equal to 0 to get any maximums or minimums. So I can rearrange this equation a little bit, start to solve this equation. So 4 pi r is 60 over r squared. Multiply both sides by r squared and divide by 4 pi. I get r cubed is 60 over 4 pi. And so r is the cubed root of just 15 over pi. So just simplifying that, 60 over 4. And we end up here that if you put that into a calculator, r is equal to 1.68 meters. So that's the radius of the cylinder that is going to optimize my surface area. Now let's check that this is in fact a minimum, because if it was a maximum, we would be in a lot of trouble. So we need to get the second derivative of the surface area with respect to the radius. So we want to differentiate this again. So we get 120 r to the minus 3 plus 4 pi. And if we substitute in 1.68 into here, you can check it in a calculator, and I recommend you do. You end up with 37.9, which is greater than 0. Therefore, we're looking at a minimum, which is exactly what we want. So this radius here minimizes the total surface area in my cylinder. Now, what would the height be if the radius is 1.68? Well, remember earlier up here, h is equal to 30 divided by pi r squared. So h is equal to 30 divided by pi times 1.68 squared, so the radius we worked out that minimized the surface area. And again, pop that into a calculator, and you should check that you end up with 3.38 meters. So your cylinder looks something like this. This is what the water tank looks like. We've got a radius down here of 1.68 meters and a height here of 3.38 meters. And we can check that the volume of this cylinder, which is given by the expression V equals pi r squared h, well, if I just substitute my radius and my height into this equation, you should see that you end up with 29.97 cubic meters. So I'd encourage you to check that in a calculator. And for the purpose of just a couple of decimal points of rounding error, this is well close enough to 30 meters cubed. So we've maintained the required volume for the water tank with these dimensions. Now let's check the surface area. Well, surface area is 2 pi RH plus 2 pi r squared. And again, substitute the value for r and h into this equation, and I'd encourage you to do it. You should end up finding that your total surface area is 53.41 square meters. So this is a minimized value for the surface area, i.e. if we change these dimensions the slightest amount, we're going to increase that surface area again, which is going to cost Hugo more money in painting the outside of this cylinder.